All right, now it's good. So good morning, everyone. We're going to continue with where we finished last time. And I realized that there were two things that I forgot to mention, or probably I gave for granted, and it wasn't that well explained. And that was about what would be the direction of a horizontal well for doing multi-stage hydraulic fracturing if we knew what is the minimum horizontal stress direction. And I just wanted to clarify that before we move on, because that's going to be something very important. So in this case, in the Permian Basin, we're saying particularly that the minimum principal stress is heading in direction north-south. And the choice for our horizontal wellbore was north-south too. And let's see why that's going to be the case. So in order to do that, I'm going to make here, try to make a three-dimensional simplification of the subsurface, where in a specific formation at a given depth, we want to do hydraulic fracturing. And in this case, this is the direction of the north, this is the direction of the east, and the depth is increasing going downwards. So we were saying that for this particular case, the minimum horizontal stress was oriented in this direction. That the maximum horizontal stress was in this direction, and the vertical stress, it's vertical. So if you were to do in this case a vertical wellbore that then extends laterally into direction east-west, something like a wellbore that goes like this, and let's imagine that goes out of that block. If you start to do hydraulic fracturing in stages like these points, based on what we said before, we would expect those hydraulic fractures to be perpendicular to the minimum principal stress direction, right? So if those fractures are perpendicular to the minimum principal stress, then probably they will start forming like discs that are perpendicular to the direction of the minimum principal stress. So these will be planes which are on the VE plane, and as they start growing, they will start growing, and at the point they are all going to be in the same plane. And because they are all in the same plane, at the end they're just going to make one big fracture but it's going to be all in the same plane. And as we were saying before, that's going to be always perpendicular to the minimum principal stress, which in this case is horizontal. So this is a plane which is more or less now perpendicular to you on the plane of the screen, and perpendicular to this direction. So that's not really efficient, because you're doing this long horizontal well, and at the end of the day you put multiple stages, but then you just have one big fracture, and that's not really ideal. What is ideal, in order to have more specific surface, more connection from the wellbore with the formation, is to have multiple fractures which are independent from each other. So in that case, what it is more efficient to do when you drill a wellbore and after you do hydraulic fracturing will be to drill another wellbore but when it gets into the formation, it kicks into a horizontal wellbore in the direction of SH mean. Now this new horizontal wellbore, if you have several stages, those fractures are going to grow perpendicular again to the minimum principal stress direction, and they're going to propagate into more or less independent fractures. To tell you the truth, nobody so far knows for sure very well what's going on in the subsurface, where fractures specifically go, if they bifurcate or if they coalesce later, if there is just one fracture, 2 or 3 fractures. Actually, Javier and I now are working in a project that is trying to investigate that and see what these fractures really look like. But for now, let's assume the simplification that these are all single fractures, something that has been assumed for a long time. And all of these fractures are going to be independent from each other. And because they are all independent from each other, the surface of those fractures in contact with the formation is going to be much greater than the one of a wellbore drilling direction east-west. So let me add a few notes here. This will be a horizontal well in direction north-south. This will be a horizontal well in direction east-west. And it's not only the amount of surface that you create which is higher, but also you make it easier for fluids to get into a fracture and then into a formation. For example, if I had a molecule of fluid which is somewhere over here and it needs to get to the wellbore, it will have to go all the way to the fracture and then go into the wellbore, right? On the other hand, if you have a molecule of fluid at the same distance, but now in this wellbore, instead of going all the way through the fracture to the wellbore, like this one, first it will go to the fracture, to the nearest one, and then through the fracture will go to the wellbore. So that's going to be a lot more efficient and a lot faster for that hydrocarbon molecule to get into the well. So that's the reason why we will drill these wellbores in the direction of the minimum principal stress. And we're going to see a lot of these. This is just an introduction, but later we're going to talk a lot about this. Yes?
So you said this is more efficient when it goes into the crack and then to the wellbore?
Yes, because it's a shorter path. Do you see why or not? If not, just let me know. I'll explain that again. Probably, let me do a top view will be easier. In a top view, if this is the wellbore which is east-west, and if this is a wellbore which is north-south, in the wellbore east-west, the fracture is on the same plane of the wellbore. So when you look at from the top, it's just something wait a minute, this is okay. So the fracture is going to be there, and in the wellbore north-south, you have several fractures like this. So again, if we draw that molecule of fluid at a distance somewhere over here, you need to go through low permeability rock all the way over there. However, if more or less at the same distance in this wellbore, you need to get into the wellbore, the high resistance path or low permeability rock path is just going to be this one, L1, which is going to be much shorter than L2. And because that's going to be shorter, it's going to be a lot easier to get there. So you may think of these as the equivalent hydraulic fractures of highways, right? You want to get to a place, and it's going to be, in most cases, highways are more or less not too busy, that there is no a traffic jam. It's going to be a lot easier to go through a highway than through the inner roads, because you're going to be more traffic, it's going to be slower, and that will be the equivalent of a tight rock. In a tight rock, it's going to be a lot more difficult, or it's going to take a lot more time to get from one point to another. But if you take a shortcut, or if you take a high permeability conduit, then it's going to be a lot easier. And that's why we have fractures in there, because they help us reduce that time so the fluid can get into the wellbore very quickly. And the distance from here to here, from the fracture into the wellbore, we make sure that that's something that is going to happen very quickly, because that's why we put propans in the fractures, and anyways the conductivity of fracture is a lot higher than the conductivity of the matrix of the rock. Any other question? I'll give you time while I work on my art here. So this is going to be the rock that is being fractured. Okay, if not, let me show you an actual example of this and what we have seen before. If you can even use this in your phones. If you Google RRC space GIS, it's going to take you to this website. This is the GIS viewer of the Railroad Commission of Texas. So the Railroad Commission is the agency that controls how much oil is produced and get revenues for that. And you may think, why is it called Railroad Commission? Well, but before, beginning of the century, the oil was moved mostly through the railway. So that's why they get started with this, and they continue. It's still called Railroad Commission. But what I want you to look at here is we have this website. We have an inventory of all the wells drilled in Texas and information of some of those wells too. What we're going to do now is we're going to zoom in and see what's going on in the Permian Basin. And I don't know if you guys, probably when you were born, there was already, probably not at the moment, but you grew up with Google Maps. But I didn't. So when Google Maps arrived, and you could see, like, just open a browser and like zoom in into a place and just see what's going on surface. That was really fantastic. It was a game changer. And here you have something similar, which is relatively new. I think this was put in the last 5 years, something like that. So we're going to zoom in the state of Texas, and we're going to get closer to the Permian Basin. Have you guys gone to Permian Basin? Midland, Lubbock? Yeah. Anyone did an internship somewhere over there? You did, Gabby? You did also, Mr. Fowler? Okay. Where were you guys?
I was in Midland. It was like a small town called Goldsmith.
Okay. Mr. Fowler?
Andrews, Texas, a little bit north of Midland.
Okay. Okay. So here, I want to zoom in specifically in a county which is Reagan County, because there is a project that was done there a few years ago to actually see where these fractures go, these hydraulic fractures. And I've been trying to mine some data so we can run that example in class and calculate vertical stress and things like that. And that's particularly here on the north of the Reagan County. I'm going to continue zooming in. And at some point, the well surveys are going to show up. Let's try one more. There you go. Okay? So now what you see here are the direction of the horizontal wellbores. So the points indicate where the wellbore starts to be drilled in vertical direction, and these are all the directions of the wellbores in horizontally. And you can clearly see, as we hypothesized before, given these measurements of stress, that the direction of the wellbores are north-south, and there is a reason for that. You may go to some other places around here, and the direction may not be exactly north-south. That might be caused by some local variations of the state of stress, or some other times, let me zoom in again. Some other times the lease it doesn't have the geometry to do a wellbore in the optimal direction, but you see whenever you have a space, this is what you're going to see. It's not moving. Okay, there's moving a little bit. So you see some wellbores a little bit in a not optimal direction, but you can also, I don't know, you can see the lines here, guys? No, probably you can't. But the lease in this direction is, it changed. So that's why direction changed too, because it's just not optimal to do it exactly north-south. All right, so with this, now we finish chapter number 2, all right? And I hope that you all submitted your homework. If I understand correctly, Javier is going to upload the solution tomorrow, so I hope you already submitted the homework. If you didn't, please do that as soon as possible. All right, so we're going to continue now talking about a tool which is going to be very useful for us in order to solve many of these problems. And that's going to be continuum mechanics. And in continuum mechanics, we're going to restrict ourselves to linear elasticity, which is the easiest model to handle, but still is quite informative. And the first thing that we have to do is to talk about stresses in the subsurface. And now we're going to extend our knowledge of stress not only to 3 stresses as we saw before, but now we're going to see that we have 6. So I know this is getting more and more complicated, but you will see that everything makes sense at the end of the day. And this is what is called a tensor. But let me give you a little bit of background about what a tensor is and why we need it. You will see that it's not too different from what you have already seen before. Okay, so let's get started with this. Let's imagine that we're in a given location in which you're drilling a wellbore, and we want to know some physical quantities in this particular location. Let's say that we do horizontal wellbore, as we were saying before, and we have some vertical fractures in there. All right. And let's say that at the beginning, in this particular place, we have a given value of pore pressure, and also a given value of let's leave it now, pore pressure, okay? So let's say that we are at the depth of 10,000 feet. And let's assume hydrostatic pore pressure. What is going to be the pore pressure at this place? You remember the hydrostatic pore pressure gradient, Mr. Fowler? Okay, so say again?
4,300.
Okay, yeah, 4,300. I like that number. And 4,300 psi, right? Let's extend this a little bit. What do you think the temperature is going to be at that place? Do you know what is the gradient of temperature? How much?
3 degrees per 100 meters.
Okay, so what would that give you at this particular location? So this is going to be more or less 3 kilometers, right? So what temperature? And let's say that somewhere over here also we are measuring temperature. 100 degrees, that sounds reasonable. I have a very hard time with Fahrenheit. So I will go, were you saying Fahrenheit or Celsius?
Yeah, 1 degree Fahrenheit and 100 feet.
Okay. Yeah, 100 could be also a little bit more. I remember in SI units that the gradient is more or less 20 degrees per kilometer. So here, more or less, that will be 60, and let's consider on the surface we have 20. That will be ADC. ADC probably will be more than 100 F. So let's just do this for simplicity. Let's put here 800 C, okay? And I hope that you notice that these values, we just define them with one number. It doesn't matter, there is no directionality in these values. Pore pressure is just one number, temperature is just one number. I could also, for example, measure the porosity of the rock, and that's going to be just one number, 2. And when we have a property that we can define it just with one number, that's what we call in mathematics a scalar quantity, because it just can be defined with one number and it doesn't have any directionality. Let's go with the next category. Let's say that we apply a pressure drawdown, and now we have this fluid moving in this direction towards the wellbore. The velocity of the fluid, v, is going to have some value. That will depend on the permeability of the rock, on the pressure gradient, but it's not going to be only a value, but it's going to have a direction, right? For example, I could say in this case that the velocity is going to be equal to, and now is when things change, because I cannot express that just with one number, because it has a direction. And because it has a direction now, I need a coordinate system. And that coordinate system, we're going to use the same one that we were using before, in which we have here the north, the east, and depth. And we're going to use a coordinate system, and in geomechanics we'll see that we're going to use always, and in mechanics in general, a right-handed coordinate system. That it has a specific rule. For a right-handed coordinate system, the first element is going to be your index, the second element is going to be your middle finger, and the third element is going to be your thumb. In this case, we're going to fix the first element to be the north direction, right? So if I look at the screen, north is there, that's going to be the index. The second one is going to be the east, and the depth is going to go down. So it's going to be like that. And you will see that if you use your right hand, you can make this right-handed coordinate system. If you try with your left, that's not going to work. So that's why it's called a right-handed coordinate system. So this is going to be 1, this is going to be 2, and this is going to be 3. And according to this right-handed coordinate system now, I can now write, just right now that I have a right coordinate system, the quantity of that velocity. Is it going in direction north? The velocity? From the drawing I did, it doesn't look so, right? So we'll put the 0 here, and it appears to be going in direction east-west, right? And it's actually going opposite to the direction of the east. So I'm going to put a negative sign, and probably here I'm going to put, I'm just making this up, okay? I'm going to put 1 centimeter per day. That's the velocity. And well, actually, let me put these units outside the brackets. And it's not going up or down. And so these are the units of velocity. But this is now, how is this called? You guys know how this is called, right? It's called a vector. A vector that has a magnitude and also has a direction. The vector is going to be always the same no matter what the coordinate system is, but the numerical numbers that you use to write it, those are going to change depending on the coordinate system. Can you give me another example of a vector for this particular application? Again, I'll let you think, and I'll work on making this schematic prettier. Any suggestion? Stress, no. Of a vector. That's going to be a quantity that we just can express with a magnitude and a direction. A force could be a force, but I don't see very clearly how to do an example here with force. So yes. What? No, no pressure. We say it's in a scalar. We just need one number to define it. Well, let me help you with that, because that one is not that easy to figure out. And another example could be a displacement. For example, when we make a hydraulic fracture here, and the rock moves, oh, I didn't mean to do that. Wait a minute. Okay. When the rock moves from the center where it was to a little bit to the right to have that fracture open, then that's going to be a displacement. And displacement is going to be a vector. In this case, it moved towards the east. It didn't move down, it didn't move downwards, it moved towards the east. It didn't move in direction north-south either. So let me clarify, this is v, velocity, this is u. Probably we could say in this case that it moved 0.5 inches in the direction east. So that would be another example of a vector. All right. Yes?
Are the fractures like into the page? Or
The fractures here are into the page and are like planes that are in this direction, are going in your direction. This is the plane. Because the fracture is opening like this. It's opening up like this, but it's propagating in this direction. So the plane is something like that, and it just opens up like this. All right. Well, then scalar, one number, a vector in 3 dimensions needs 3 numbers. And not only 3 numbers, but also we need the directions for those, right? And as soon as we say the coordinate system, that's already defined in there, that with those numbers we mean directions north, east, and down. All right, so the last one that we're going to see, and is the one that we're going to study in detail in this class, is stress. And stress, as we were saying before, we're going to have 3 stresses at least, which are the vertical stress and the horizontal stresses. I don't want to make this drawing too busy, but we're going to see that stress, usually we're going to denote that with a variable name and 2 lines underlining that. And if the first one was expressed with 1 number and with a vector or just 1 row, what do you think this stress is going to be written like? So before we had just an array of 1 by 3. So a vector, a tensor in 3 dimensions is going to be a matrix. And in this particular case, let's assume that we're going to use, I'm going to use now a new word that we already used, but we're going to see exactly what that means in a bit later on. We're going to assume that now we have the principal stresses of that. So here I have SV, but notice, SH mean is in this direction and SH max is in this other direction. It does matter where you write each of the variables, because now we have a direction. And if we expect this 1, 2, 3, the first element, the first row in the first column is going to be the stress that goes in direction north, which is SH max. The second diagonal element, second row, second column, is the one that goes in direction east, and that's going to be SH mean. And the third element, which is in the vertical direction, that's going to be SV. And I'm going to assume now that these are all principal stresses and all the other elements are going to be 0. And this is what we call a tensor. I remember the first time I heard about the tensor, it was in a fluid mechanics class. And I was like, what? What is this guy talking about? And it took me, some time to understand what it was. But it's actually not too difficult. It's just a quantity, a property that needs 6 values to be defined and also needs directions. And we're going to see in a bit what those 6 values are. But I see that you see now clearly the difference that we have 3 different values in 3 different directions, which are the principal stresses. So yes.
Do you have to make SH being negative or
I could, if we were talking about a stress which is in tension. In geomechanics, we're going to assume that compression is positive and tension is negative, and with the values of the stress in the tensor, we'll see that they are not necessarily aligned with the direction of the axis. So, for example, in all of these cases, it appears, that these are pointing, at least SH mean is pointing in direction negative to the axis. But you should remember that for that to be in equilibrium, there is also another stress on the other side, which is keeping that equilibrium. So the value of that stress is going to depend on whether if it is compression or tension, and if it's shear, we'll see that later on. All right? Okay, so let me say one more thing about this. What about, we said that this depends a lot on the coordinate system, right? So what about if I don't like that coordinate system and I want to use another coordinate system? Like, for example, I could do I want my coordinate system to have an origin somewhere over there and to be X, Y, Z. It's okay. It's a right-handed coordinate system, X, Y, Z, and it could be used, right? But if I write those quantities in a different coordinate system, then these values are going to change. And let me make it actually a little bit more complicated. What about if I don't want those? Let me do it with another color. I don't want to align it with the previous one, and this is going to be at some orientation that is not aligned with the vertical direction. That's also okay. You can work with that. But if you do that, if you write the stress tensor in that new coordinate system, it's not going to look as simple as the one that we just wrote. It's going to look, because those principal stresses are not aligned with the directions of the coordinate system, it's going to look like this, in which the off-diagonal elements are not equal to 0. And this is going to be in coordinate system X, Y, Z. But I hope that you notice that the tensor is the same. It's just it's written differently depending on the coordinate system that you choose. But it's exactly the same. It's the same as with the velocity. It's just that changing the coordinate system is going to change those values. All right. So now we know what's a tensor and what's the difference with a vector and with a scalar quantity. And I didn't put numerical values here, but we could put some numerical values, right? Let's do that just for the sake of completeness. We're not in a rush. There is, what would you say is the vertical stress at this particular location? More or less. You should know that by now. This is onshore, okay? Any suggestion? You remember what was the gradient of total vertical stress? One psi per foot, right? So if we have 10,000 feet of depth, then we could say that more or less the vertical stress here is 10,000 psi. And let me fill this with zeros. What about the horizontal stresses? What do you think those values are going to be? And let's assume that here we are under normal faulting conditions. And also, I hope you remember that for normal faulting, this is the condition. Okay. The horizontal stress in a place with normal faulting, it's going to depend on many things, right? And that's actually, we're going to spend a lot of time calculating this horizontal stress. But more or less, you know, for typical conditions, it's about 60 to 70% of the vertical stress. So here, I'm just, you know, estimating very roughly what the value of the minimum horizontal stress is, and let's say 7,000 psi. And we know that the horizontal stress, the maximum, has to be in between the other two. And actually, that's a very important value. What is the difference between the two horizontal stresses? That impacts a lot hydraulic fracturing and drilling and many other things. But we're going to assume that this is a relatively passive tectonic environment, so there is not a lot more of compression in one direction than in the other, but there is always a little bit of difference. So we're going to assume that there is just 500 psi of difference, and that's 7,500. So I'm just making up those values, right? But I just wanted to put some numerical values to have an idea. Okay. So now we know what is a scalar, what is a vector, and what is a tensor. Let's come back over here. So now we have a better idea about what we're looking at, and what we would like to answer now in this figure is what we know what the diagonal terms are. The diagonal terms are going to be the normal stresses applied on the face of that prism. And you can see that all those diagonal terms, S11, S22, and S33, are the blue ones, are the normal ones. The off-diagonal terms are the shear stresses. And those shear stresses, you can also see that those are applied on the faces of that prism, and they are parallel to each face. All right, so again, diagonal terms are going to be the normal stresses. Off-diagonal terms are going to be the shear stresses. And there is a convention for the direction of those arrows. And you know, this is something that I like that you know, but it's not critical. It's not going to change totally your understanding about geomechanics. But it's something that, you know, we should talk about at least once, and you should understand what it means. All right. We were saying that compression is going to be positive, right? And with this convention, that means that a value is going to be, a stress is going to be positive whenever the direction of the arrow, the direction of this arrow is pointing opposite to the direction of the coordinate system when it is applied on the opposite face of the prism. Let me say a little bit differently. If you walk a positive amount from the origin, for example from here to over there, that's going to be a positive displacement, right? Well, if you walk from here, from this face to this other face, that's going to be a positive displacement. After you do that positive walk, all the arrows in that face, in order to be positive numbers, they have to be pointing in opposite direction to the coordinate system. For example, for normal, you see it's pointing right to left. For the shear stress is pointing up, opposite to the direction 3 over here. And for this one is also pointing direction opposite to direction 1. So these are all positive. They are drawn with this convention that these are going to be positive. So for the normal stress, it's a little bit straightforward because you see they are pointing towards the object, that means compression. They are pointing away of the object, that means tension. And you know, that's easy to see. With the shear stresses, it's a little bit more complicated. But if you follow that rule, you will see that it's not that complicated after all. But there is something more important, that the direction of the arrows. What is very important is what are those sub-indices. Those sub-indices mean something. The first sub-index means in which phase the stress is applied. For example, all these stresses in here, they have a sub-index, first sub-index 2. That means they are applied on phase number 2. Which is phase number 2? Is a phase which is perpendicular to axis 2. So there is just one phase which is perpendicular to axis number 2, and it is this phase over here. In that phase, all the stresses start with S2, the first sub-index. And the second one means in which direction the stress goes. For example, for the normal is S22, is stress applied on phase 2 in direction 2. And this is the normal stress. For this shear stress, is stress applied on phase 2 on direction 1. And it's a shear stress. And this one is the stress applied on phase 2 on direction 3, and it's also shear stress. And since they have indices which are not equal to each other, that's also why they appear here in the matrix as the off-diagonal terms. So that's why they are in the off-diagonal, because those sub-indices, they are not the same. And you can see that in the other phases, the rule is always respected. Remember, first index would be the phase on which they are applied. The second one is direction. When the two of them coincide, that's what is called a normal stress, because it's normal to the surface where it is applied. And the second one means the direction. And those are going to be shear stresses. Okay. Any question about that? Let me see if I forget something. I don't think so. Oh, I forgot my toy to talk about principal stresses. All right. So you remember that we said that we could change the coordinate system and the stressor could be written differently. For example, when we were talking about this particular case, we started from principal stresses and we went to the stress tensor with stresses in all directions. Well, in general, actually, we don't find that case. It's actually rather the opposite, in which we mostly have directions in one coordinate system, and then we have normal and shear stresses. But the good news is that we're always going to find a coordinate system in which we can calculate those principal stresses. Actually, I would really like to explain and to talk about this toy. Javier, can you do me a favor? Can you bring the cube, which is the color cube, which is on my desk? Thank you. All right. So in general, we're going to have this state of stress in which we have shear stresses and normal stresses. But by using mathematical operations like eigenvector and eigenvalue, we can calculate what the principal stresses are, what are their values, and also what the directions are. So the values, let me see if I have it written somewhere over here. Okay, well, it's written right here. The values of the principal stresses, that's something that you calculate with something that, an operation that we call eigenvalue of a matrix. And the direction is calculated with another function which is called eigenvector. I don't know if you can do this in Excel. Probably you can, but I have never done it in Excel. But in Python, in MATLAB, you can do that very easily. Eigenvalue, eigenvector of a matrix, and you get that right away. Okay. So, physically, then, when we calculate those principal values, those are going to mean that those are values with associated directions in which there is just normal stress. There is no shear stress. If you were to see the stresses in some other direction, you will see actually there are shear stresses, but there is just one direction in which you will just see normal stresses and no shear stresses. And mathematically, we see that as a matrix in which we just have values in the diagonal and no or zero values in the off-diagonal terms. That means that in this condition, those shear stresses are zero. And in general also S1, S2 and S3 are different. Something which is very nice about this is that whenever we compute these eigenvalues, given the properties of a tensor, those are going to be real numbers. If you put, for example, a matrix which is not symmetric, probably you might not get real numbers as eigenvalues. You get a complex number. And that's a property which is due by something I forgot to tell you, but probably you more or less presume that that was true. And is that this stress tensor, and then we get to something very important, is symmetric, which means that the value of S21 is equal to the value of S12. The value of S31 is equal to the value of S13, and the value of S32 is equal to the value of S23. And if you remember when I was telling you that we need 6 values, where there you have those 6, because the matrix has 9 values, but there are 3 which are the same. So at the end of the day, we just have 6 values which are different. All right, while we wait for Javier, let's see why those values are the same. Those values are the same because of, thank you very much, Javier. Those values are the same because of equilibrium conditions. I'm not drawing in this schematic what is the stress on the hidden face of the cube, but you could imagine that for this to be in equilibrium, there should be another stress in this direction, which is, let me use a pointer because I think that appears in the video recordings. Okay, the stress in this direction, there should be an S22 also in this direction, which is stopping that cube to go to the left. Otherwise it would move. But no, this is in equilibrium, so there has to be another stress which is exactly the same in value on the other side. And with shear stress is going to happen the same. For example, let's take a look at S23. And let's say all the other ones are 0. S21 and S13. If I have S23 applied on this face going up, that means that there must be on the other side a shear stress which is going down. And if it's going down in the other face, you may think that this is going to apply a torque which is going to make all this cube to rotate counterclockwise. But that doesn't happen. Why? Because there is another torque given by S32, which is equal in magnitude, but makes the cube try to rotate in clockwise direction. Actually S32 over here, and the other one that you can see going in direction to the left. And for that torque, in order to be the same, S23 has to be the same as S32. And that's why that's a symmetric tensor. All right, so let's talk about one more example about what is a principal value and the analogy with this cube. Okay, so I hope this works and it switches to the video. Let me turn on this. Hopefully it will get recorded, and I'm going to put this cube over here. Okay, don't look directly at the cube, okay? That will be cheating. Can anyone tell me what's the color of this cube? How many colors it has? Let me point in a direction that is perpendicular to the axis of the camera. All right. So how many colors would you say? It looks, yeah, like, let me, oh, let me use this. So if we look at the, we have here apparently yellow, green, light blue, violet, pink, red, orange, a dark green, light green. So there are quite a few of colors, right? Well, we see all those colors and all those combinations because we're looking at the direction in which it's not the one that reveals the true colors of this cube. I can rotate this cube, and if I look at it in the right direction, I will just see. Let me turn off the light. Let's see if that helps. Okay, well, a little bit better. There's just one color. It's blue. When you look in this direction, it's just blue. When you look in this direction, it is just pink. And when we look in this direction, it's just yellow. So there are actually 3 colors of the cube. But it depends on which direction you look at, and you will have more colors or more combinations. But the true nature of the cube is just 3 colors. And it's exactly the same with the stress tensor. If you look with the right coordinate system, you will get just 3 values, the principal stresses. But you have to find those directions, right? But you can do. It's just a mathematical problem. If you look at it, or if you write the tensor in a coordinate system which is not the principal coordinate system of that tensor, then you will see many values. So these are called either principal values or eigenvalues, and that means like something which is it's a property of the tensor. It's something inherent to the tensor, that principal value or that eigenvalue. Is something which is, like, as I was telling you before, for this cube, is like the true nature of that tensor. And those are what we call principal stresses. All right, so let's see, we're getting close to the end, and I think there is some heavy math here, and then you may be already a little bit tired, and we also have many people absent because they are in the Engineer Expo, so we'll just finish here. And good news for you is that there is no homework this week due next week. The next one is going to be due about 10 days from now. Okay? All right. Thank you, guys.